In this module, you will learn about the characteristics of electromagnetic radiation and Planck's quantum theory. We have already learned that the Rutherford's nuclear model of an atom basically suffers from major drawbacks, which are as follows. Firstly, it couldn't explain the stability of an atom in the view of the electromagnetic theory. Secondly, as a consequence of its inability to explain the stability of an atom, it couldn't explain the observed atomic spectra. This is because, according to the electromagnetic theory, an accelerated electron continuously emits energy, and ultimately it falls into the nucleus along a spiral path. As the electron is emitting the energy continuously, the spectra of such an atom also should be continuous. But the spectra of elements indicate that atoms emit energy discontinuously, and hence the Rutherford's atomic model couldn't explain the observed spectra of atoms. Another drawback is that it could not explain the electronic structure of atoms, that is, the distribution and energies of electrons in an atom. These drawbacks inspired several scientists to revisit the historical results about the behavior of electromagnetic radiation and its interaction with matter in order to improve the Rutherford's atomic model. The improvised outcome of the Rutherford's atomic model is the Bohr's atomic model. Bohr's theory could successfully explain the stability of an atom as well as the discontinuous spectra for hydrogen atom. To understand the Bohr's atomic model, it is necessary to first acquaint ourselves with the nature of electromagnetic radiations. The underlying principle behind the Bohr's atomic model is the quantization of energy, which is explained in the latter part of our discussion. Energy can be transmitted through space by electromagnetic radiations. These electromagnetic radiations are the best described in the terminology of waves. The wave nature of electromagnetic radiation was established in 1870 by James Clerk Maxwell. Let's now understand the general characteristics of waves. An object produces a series of waves when it vibrates continuously. However, the vibratory motion of charged particles, like electrons, produce a wave train of oscillating electrical field and magnetic field. Such waves, which are produced due to the periodic motion of charged particles, such as electrons, are called electromagnetic waves. This is suggested by James Maxwell. Note that the name electromagnetic radiations is attributed to the waves that consist of oscillating electrical and magnetic properties. An electromagnetic wave can be represented as shown. To characterize a wave, we need to specify its properties, such as wavelength, frequency, and wave number. A wavelength is the distance between two successive crests or troughs of a wave. Wavelength is denoted by the Greek letter lambda. It is expressed in either centimeters or meters or in angstrom units. The next characteristic of a wave is the frequency. Frequency is the number of waves that pass a given point in 1 second. It is denoted by the symbol nu and is expressed in hertz. Velocity of a wave is defined as the distance travelled by a wave in 1 second. Velocity is denoted by c and is expressed in centimeter per second. Let's now understand the relationship between the wavelength, frequency and velocity of a wave. As frequency is the number of waves passing through a point per second, and wavelength is the length of each wave, their product will give the velocity of the wave. The electromagnetic waves travel through empty space with the velocity of light. The last characteristic of a wave is the wave number, which is defined as the number of wavelengths per unit length. It is denoted by the symbol nu bar and given by the equation nu bar equals 1 by lambda per centimeter. Now, let us solve a numerical problem on the basis of the characteristics of a wave. Calculate the wave number and frequency of violet radiation having wavelength 4000 angstrom. First, let us calculate the wave number. The first step involves writing the formula to calculate wave number, that is, nu bar equals 1 by lambda. The given lambda value is 4000 angstroms, which is equal to 4 multiplied by 10 raised to the power of -7 meters. The second step involves substituting the value of lambda in this equation. On solving, we get nu bar is equal to 2.5 multiplied by 10 raised to the power of 6 per meter, or 2.5 multiplied by 10 raised to the power of 4 per centimeter. Now, let us calculate the frequency of violet radiation. The first step involves writing the corresponding formula nu equals c divided by lambda. The second step involves substituting the value of lambda, that is, 4 multiplied by 10 raised to the power of -7 meters, and velocity of radiation, which is equal to 3 multiplied by 10 raised to the power of 8 meter per second in the above equation. On solving, finally we get 7.5 multiplied by 10 raised to the power of 14 per second. Now, let's look at certain key properties of electromagnetic waves. Electromagnetic radiation, as shown, is a form of energy that consists of alternating electrical and magnetic fields produced by oscillating charged particles, are perpendicular to each other and perpendicular to the direction of propagation of radiation. Unlike sound or water waves that require a medium for propagation, electromagnetic waves can move in vacuum at the velocity of light, that is, 3 into 10 raised to power 8 meters per second. All electromagnetic radiations travel with the same velocity but differ from one another in wavelength and therefore in frequency. Let us have a look at the arrangements of different electromagnetic radiations in increasing order of their wavelengths or in decreasing order of their frequencies. When these electromagnetic waves of different wavelengths are arranged in the order of increasing wavelength or decreasing frequencies, it is called electromagnetic spectrum. Of these, The radiations that are visible to the naked eye constitute the visible spectrum. The frequency range of the visible rays is 3.9 into 10 to the power 14 to 7.9 into 10 to the power 14 Hz. The region above the violet color is called the ultraviolet region and has a frequency equal to 7.9 into 10 to the power 14 to 3.4 into 10 to the power 16 Hz. The region below the red color is called the infrared region, and the frequency of the waves of this region is 3 into 10 to the power 11 to 3.9 into 10 to the power 14. Ultraviolet and infrared rays are not visible to the naked eye. Other important regions in the electromagnetic spectrum include radio waves with frequency less than 10 to the power 9 and microwaves with frequency of 10 to the power 9 to 10 to the power 11 Hz. Radio waves have the longest wavelength in the electromagnetic spectrum. Radio frequency region around 10 to the power 6 Hz is used for broadcasting. Microwave region around 10 to the power 10 is used for radar. Two other kinds of electromagnetic waves are X-rays and gamma rays. The wave nature of electromagnetic radiation successfully explains the phenomena of interference and diffraction. But the phenomenon of black body radiation, photoelectric effect, and the spectra of atoms were not explained. These things could be explained only if the radiation is assumed to be a stream of photons. That is, by considering particle nature. Let's understand these phenomena one by one. First, let us understand the phenomena of the black body radiation, which was given by Max Planck in 1900. In general, when radiation strikes any surface of the body, part of it is reflected, part of it is absorbed, and part of it is transmitted. For example, when an iron rod is heated, at first it turns red. As the temperature is further increased, it becomes yellow, then white, and finally turns blue. This actually shows that the radiation is emitted in the order of increasing frequency, red light being of lower frequency and blue light being of higher frequency of visible region. On the contrary, an ideal black body is a perfect absorber and emitter of radiation. A blackened metallic surface or a hollow sphere blackened inside with a small opening behaves almost as a black body. Any type of radiation that enters this small opening gets reflected multiple times within the sphere until all the energy is absorbed. Thus, a black body is not only a perfect absorber of radiant energy, but also a perfect radiator. Black body radiates the maximum amount of energy at a given temperature. Note that it radiates the same amount of energy it has absorbed. From the graph shown here, it is visible that at a given temperature, the intensity of radiation emitted increases with decrease in wavelength, reaches a maximum value at a particular wavelength, and then starts decreasing with further decrease in wavelength. We have seen that at a given temperature, there is a wavelength at which the maximum intensity of radiation is emitted. But the position of this maximum intensity shifts towards higher wavelengths with decrease in temperature. These observations could not be explained by the electromagnetic wave theory of light. To account for these experimental observations, Max Planck in 1900 proposed that radiant energy is emitted or absorbed discontinuously in the form of discrete packets or bundles of energy and not continuously. This is the first postulate of Planck's theory. Further, Planck called these discrete quantities or packets as quanta. Quantum is the smallest quantity of energy absorbed or emitted in the form of electromagnetic radiation. This means that the light radiations absorbed or emitted by atoms or molecules comprise a stream of quanta, but not continuous waves as shown. According to the second postulate, the amount of energy associated with the quantum of energy is proportional to the frequency of radiation. E is proportional to nu, or E equals h multiplied by nu, where E is the energy of the radiation, h is the Planck's constant 6.625 into 10 to the power of minus 34 joule/second, and nu is the frequency of radiation. To write this equation in terms of velocity and wavelength, substitute the equation 2 that nu is equal to c divided by lambda in the above equation. Hence, the resultant equation is E is equal to h multiplied by c divided by lambda. The third postulate says that the total amount of energy emitted or absorbed by a body will be a whole number multiple of quanta. That is, E is equal to NH nu. This means that an atom or molecule can absorb or emit either one quantum of energy or any whole number multiple of quanta. Note that only certain values of energy are permissible. This is called the quantization of energy. Now let us solve a numerical problem based on Planck's equation. Calculate the magnitude of the energy of 1 mole of photons of radiation whose frequency is 4.96 multiplied by 10 raised to the power of 14 per second. The first step involves writing the expression for the energy associated with one photon, that is, E equals h nu. In the second step, let us substitute the values of h, that is, 6.626 multiplied by 10 raised to the power of minus 34 joule/second, and the given value of frequency, that is 4.96 multiplied by 10 raised to the power of 14 per second. On substituting and solving, finally, we get 3.286 multiplied by 10 raised to the power of minus 19 joules. The third step involves writing the expression to calculate the energy associated with 1 mole of photons. That is, E equals NH nu. Here, N is equal to 1 mole, that is 6.023 multiplied by 10 raised to the power of 23. On substituting the value of N, H nu, in the equation and solving, we finally get E equals 19.788 multiplied by 10 raised to the power of 4 joule per mole, or 197.882 kilojoule per mole. You have now reached the end of this module. In this module, you learned that line spectra could not be explained using the Rutherford's nuclear model. In 1864, James Clerk Maxwell established the wave nature of electromagnetic radiation. Characteristics of waves are associated with wavelength, frequency, velocity, and wave number. Electromagnetic radiations travel with the same velocity but differ from one another in wavelength and therefore in frequency. Their wavelengths increase from gamma rays to X-rays to ultraviolet rays, visible rays, infrared rays, microwaves to radio waves. When these electromagnetic waves of different wavelengths are arranged in the order of increasing wavelength or decreasing frequencies, an electromagnetic spectrum is formed. Wave nature of electromagnetic radiation explains interference and diffraction, but could not explain blackbody radiation and photoelectric effect. In 1900, Max Planck established the Planck's quantum theory that states that radiant energy such as light and heat is propagated in the form of small packets called quanta. The amount of energy associated with the quantum of energy is proportional to the frequency of radiation, E is proportional to nu, or E equals h multiplied by nu.